Hi, welcome to Product Review by Watt Hour. In this video we are going to do the review of this boost converter with a rated power of 400 watts, maximum voltage of 60 volts. I'm also going to explain the major components. We are going to test and see what is the minimum voltage that you can get from this and what is the maximum voltage, and we will feed different voltages and we will check all the currents. Also, I'm going to try to show you how to set the current limit using this if you want to use a battery to charge it. From time to time I'm going to use a thermal camera to show you which spot of the device is getting hot. You can set the current limit. You can get the data sheet and other files related to this by visiting our website watthour.ca. We have an input here, the two terminals for the input, and two terminals here are the output. At the input also we have a 15 ampere fuse. This is those fuses that are used in cars and high current modules. And then the main inductor. So from here, you know, with the inductor and the fuse, that is the input. And the output also. And this side, this is the multi-turn potentiometer for constant current, and this is for constant voltage. First, let's see the specification. Do not worry about this 400 because it will not be true in many cases. Input voltage 8.5 to 50 volts, so we cannot go below 8.5, and maximum 50. And here input current, this is very important. It says 15 ampere, that's maximum, and if you go above 8 ampere then enhance the heat dissipation. So we have to put extra heat sink, otherwise with the current state we will get only 8 ampere. And output voltage can be up to 60 volts. Whatever you input, you always get higher. And then constant range, the current that you can set is between 0 to 12 ampere at the output. Operating frequency, the switching frequency is 150 kilohertz, and the efficiency we are going to test it, very important. Doesn't have input reverse polarity protection. And on AliExpress, if you just type DC 400 watt 15 ampere boost, you get this results, and the prices are in Canadian dollars. For example, this is $9, around $7.50 or $8 US with some shipping. There is some sale going on, so this is the same module that is red and has only these two capacitors and vertically one of the stores. Get it in 60 days, but if you pay a little higher you can get it between 60 and 6 days. A little higher you can get it, for example, $7.78. You can get it at 15 to 30 business days. This is the input labeled as N plus, N minus, and we have a 15 ampere fuse at the input, so you will not make mistake. On this side we have no fuse, and the inductor. So inductor and fuse are at the input side, and this is the output. It just says plus and minus, and these two capacitors are at the output filter, and they have been rated 63 volts. What it means is that if you set the output above 60, which when I tested it was possible to do it, these will explode. They can handle it for a few seconds and then explode. So be careful. These are the most vulnerable pieces that we have. We have two heat sinks here. We have only one main chip here. These are just two transistors. Let's have a look at them. 4 screws so that we can install it. The two heat sinks have been screwed here with the 2 screws on this side and 2 for this one. This fuse died, and I have to remove it by desoldering it from here, and I have to solder this. This should have been just a socket, so you could remove it easily, but they did not bother to put the socket there. Length of the module is 67.3 millimeter. The width is 48.1 millimeter. Height of the module is 27.6 millimeter. And if you're concerned with weight, it's 85.1 grams. Let's have a look at them. Let's have a look at this piece first. And this is TL494 from Texas Instrument. TL494 is 40 volts, 0.2 ampere, 100 kilohertz pulse modulation controller. Let's have a look at this piece here. And as you can see, that is NCE8290. And here's a datasheet for NCE8290. It is an N-channel enhancement mode MOSFET. The maximum current is 90 ampere at 82 volts. And this drain source resistance is 8.5 milliohm at 10 volts. And let's have a look at this one. And this is MBR20100CT. And here's the datasheet for MBR20100CT. Dual Schottky diode. Maximum current it can handle is 20 ampere. Let's have a look at this resistor here. And this is 0.01 or 10 milliohm resistor. All the current passes through this, and the system decides to know how much current goes. Let's have a look at these two small pieces. Both of these are labeled as Y1 and Y2. And here is a data sheet for this Y1. It is a silicon planar voltage regulator diode. And here is Y1. And the Zener voltage is 10.2 volts. And Y2 is SS8550 NPN general purpose transistor. And here is the packaging. It says Y2. Let's check the minimum voltage that we can connect. So this is input voltage. It is 12 volts and the current shows 10 milliampere already connected. Output voltage, you see it here, is 45. We can change the voltage from here, but pay attention, this is reverse. So when you go counterclockwise, it will increase. So now they mentioned 60 volts, but when I wrote it, it seems it is increasing. And if I continue doing that, it might damage it. So I'm not going to go above that. So right now it is 60 volts. Let's see what we get with the 12 volts. I'm going clockwise to reduce it. 0.1. What is going on? Something is wrong. So 11.8 it shows now. But if I turn it on, let me put the 2 ampere. Actually, we are reducing now. Now it is reducing it from 12 volts to 11.4. But I would advise against it. Here is the current, input current. Now let me show you how we can set the current limit. You need to have two parameters for the current limit to set. You need to know the voltage. In this case, we want to set the voltage to 15 volts, and we want to set the current for 3 ampere. And this is my electronic load, and this is my electronic load. I'm connecting my ampere meter at this point. This is the electronic load DL3031, and these are the two terminals that from the circuit will be connected in here, and we will see the voltage here and the current. The volt and ampere is shown here. So in this case, I'm connecting that. In your case, you will get your you will get your ampere meter, you will set it to maximum of 10 ampere or whatever you have. So more than 10, it should be 10 or more, and then connect this positive from here to there, and then the two terminal will be connected at the output. First, let's set the voltage, 15 volts. So I'm rotating this to reduce the voltage. I'm rotating it clockwise because currently it's set to 19. Okay, so we set it to 15 volts. Now this is now set as a constant resistance, and this electronic load is now acting as 5 ohm resistor. So in this case, Ohm's law says that I is equal to V over R, 15 divided by 5, it will be 3 ampere. So when I connect it initially, it will draw this electronic load, will take 3 ampere from here. So let me turn it on. And as you can see, the Ohm's law is working, and it is 3 ampere from this module goes to the device. And now I will reduce it and make it 2 ampere because we need 2 ampere. So we set the current using this potentiometer or variable resistor, and in this case this works properly. Counterclockwise means reduce. So I'm reducing it and reading. As the current is reduced, the voltage also will be reduced because it's below 3 ampere, and the voltage should be reduced because the job of this is to reduce the current and keep the current at the level that we want. I'm going now 2.7, 2.6, 2.5, 2.3. So I've set it now to 2 ampere. If I turn it off, it shows that the voltage is 15 volts of this, but because the current is set to 2 ampere, when we turn it on, this doesn't allow anything above 2, so it allows 2 ampere by keeping the voltage down. So that's why it reduces the voltage, and this is how constant current works. So you can do the same thing for the battery as well, which I'm going to show you next. Now let's start the tests. I'm reading the input voltage and current in here. The output voltage and current will be here, so the power enters, and from here it exits and goes to my electronic load, and we will be reading the current and voltage in here. Also the power will be displayed. 9 volts, output is 12 volts. Let's go with 2 ampere. I'm increasing it with 3 ampere. Output is now 3 ampere, and you can read the current. Let's go 4 ampere. So we can let's go with 5 ampere. And as you can see, the input current is 7. And this is very crazy. When they mentioned the input current above 8, you need extra heatsink. So input is now 7. I have to pay attention to this. Now let's go. Already 9 ampere. And this fuse is 15 ampere. So the voltage has dropped a little. Six ampere, 12 volts, 71 watts. Let's go. 7, and input is now 10 ampere. It's very normal. A little warm, but not hot. And here is a thermal image, and as you can see at this spot, this is a little warm, 35 degrees at this spot. The voltage got dropped, which means this cannot handle it. Let's reduce it to 6. So 6 ampere is okay with 12 volts. And if I rotate this thermal image, so here this area is 51 degrees. Nine volts input, 12 output. As you can see, the voltage is dropping. With 6 ampere, we are getting 87% efficiency. Now input is 9 volts, as you can see, and the output is 15 volts. Let's go with 6 ampere as before. Input is now 11, so we cannot continue like this because it will heat up slowly. Now it is heating up. Very hot. And here is the thermal image. At the middle here it shows 55, and here now input is 9 volts, output is 24 volts. Let me go with 3 ampere. So now output is 3 ampere, as you can see input is 9 ampere, and we are not allowed to go above 8. They say maximum 15, but heat up very quickly. So you can get, as you can see, it is 72 watts. And if I go 4 ampere, the input is very high, 12. With the 9 volts input, 24 volts output with 3.5 ampere. Input current is 10.57 and the efficiency is 88%. Now input is 9 volts, output is 36 volts. Let's go with 3.5 ampere. And it goes to 16 amp. So let's go with 2 ampere. So with 2 ampere at the output, as you can see, we are getting 8.9 ampere. I'm not going to go above this. With 2 ampere, 36 volts, efficiency is 89%. Input 9 volts, output 50 volts. Let's go with 1 ampere. As you can see, the input current is now 6. I'm watching it. As soon as I went 2, it became 13. So I cannot go there. So I'm adding just a decimal. So 1.1, 1.2, it's 7. 1.3, 8 ampere. and efficiency is 88%. And now input is 9 volts, output is 60 volts. Let's go with 1 ampere. So as you can see, we are getting at the input 7.6 ampere, and I'm watching it. Let's add 1.18 ampere. If I go 1.2, that is 9 ampere. 1.3, 10 ampere at the input. And here is a thermal image, 61 degrees Celsius. (64), it's increasing. (65). This spot right in here, this is the hottest. Right now efficiency is 85%. Let's have a look at the thermal image. And it is 68 degrees Celsius at this spot. Very hot. And her input is now 12 volts, output is 15 volts. Let's go with 5 ampere. So now it's 6.8 ampere at the input. I'm watching it. We go up to 9, so that's 9.7. Efficiency is now 90%. Input is now 12 volts, output is 24 volts. Let's go with 5 ampere. It's 11 ampere, so we cannot go. And input is now 11.2 ampere. Let me reduce it. So we can go 8.84 or 9 ampere. 96.5 watts. Efficiency is now 91%. Input is 12 volts, output is 36. Let's go with 4 ampere. And as you can see, it's 13, so let me reduce it, make it 10 ampere. With 3 ampere at the output, with 3 ampere output, 36 volts, input is 10 ampere, efficiency is 91%. Input is 12 volts, output is 50 volts. Let's go with 3 ampere. As you can see, it is 14 ampere. Let me reduce it because the fuse will blow out. Now it's 9 is okay. So we can get 50 volts, 2 ampere at the output, while the input is 12 volts. 9.2 ampere is the input current. Efficiency is now 90%. Now input is 12 volts, output is 60 volts. Let's go with 2 ampere. It is 11 ampere at the input. Let me reduce it. 1.9. So we can get 1.9 at 60 volts. And efficiency is now 88.6%. Let me show you the thermal image. It's getting hot, 67 degrees Celsius, 68. Exactly at this spot. This chip is getting hot the most. Now 72 degrees Celsius. The temperature is increasing. Let's see on this side. What is the hottest spot? 65 degrees. Now input is 24 volts, output I set it to 36. Let's go with 2 ampere. So it's very little for the input now. Let me increase it. I'm watching it, make sure it doesn't go above 9. So that's 9.7. If I go one more, it will be above 10, even 11. So let's keep it 9.5. So we can get 6 ampere 36 volts. That's 216 watts, 216.7. You can see we are getting 230 watts at the input, and efficiency is now 94%. Efficiency increased. The reason for that is that we increased the input voltage. Input is 24 volts, output is 60 volts. Let's go with 4 ampere. So we are getting 10 ampere if we accept that. 260 watts is the input and 241 is the output. Efficiency is now 92.6%. Now input is 36 and output is 50 volts. Let's go with 2 ampere. And here we are reading 5 ampere at the input. Let me slowly increase this 1 ampere, and this is now 4. This is now input, output is 4, and this is 5. Let me go 6. Now I'm just looking here, 8 ampere. So now we are 10 ampere, and as you can see, we have reached 370 watts. This is still beyond 8 ampere. Efficiency is now 95%. Amazing. Let me show you the thermal image. The hottest spot is here, 69 degrees. What is that? This resistor, the shunt resistor, is getting hot the most now. And as you can see, it is reducing the output voltage. As soon as I made it 6, so 6 worked. As you can see, the voltage is being reduced because of the heat. Let me reduce it. As soon as I made it 6, the output is back at 50. Efficiency is still 95%. Now input is 36 volts, output is 60 volts. Let's go with 4 ampere. As you can see, we are getting 7 amp. Let me increase it to 5, and it is 8 ampere. Let's see if this can hold and how is the heat. Let me show you the thermal image. 72 degrees at this spot. Let's pay attention. And here is the room temperature, 24 degrees. 117.5 watts is the input. Now with 5 ampere, 60 volts with the input of 36, and efficiency is 94.6%. 60 volts because at 5 it was heating up. So 4 ampere, 60 volts with 7 ampere at the input at 36 volts. Efficiency is 94.7%. Now let me show you how we can charge the battery. This module cannot charge one cell battery or even 2 or 3 cell. It should be at least 3 or higher to charge it because the output is minimum of 10 volts. So this cannot be done, but we need to know 2 parameters for the battery. You need to know the voltage of the battery and then the current. To charge multiple cells that are connected in series, this is not a good option because this is not balanced charger, or this cannot know the voltages across all of this, because this has only 2 wires. So if I connect this at the beginning and end, all the other cells we don't know. You need proper charger, BMS, battery management system. I have separate video explaining this. The link is below the video in the description. This has separate wire for each battery, and you will connect it, and it will monitor the voltage, and it will turn it off for that specific cell of the battery. One of them gets charged early, the other gets charged later. And in this case, let's say this is a lead acid battery and it's only one piece. You can charge it from here, but you can charge it using this, but it is not a proper way to charge the battery. Let's do it. For each cell, this is 4.2 volts, 4.2 times 4. The voltages now for 4 cells will be 16.8. So we have to set at 16.8, and then the current will be 2 ampere. Let's see. So the voltage is set to 16.8. Now the current, again, you will turn this counterclockwise, connect your ammeter, turn this fully counterclockwise, set this to maximum current, let's say 10 ampere or whatever you have, and then connect this probe to the 10 ampere terminal. And now this is acting like a short circuit. You cannot measure voltage with this, so you just connect it at the output terminal and it will read the current for you. And here I'm connecting the 2 terminals in here, and as you can see, it shows 12 ampere. This counterclockwise, until you know it's at the end. And I'm trying now to get the current. When I connect it, it goes 12 ampere. This is huge. Now it looks very crazy. If I connect this, as you can see, it shows 12 ampere. It's huge. And I don't know if I have a chance even to rotate this to reduce it, because the module might die. Let me put this so you can see it. So I'm doing counterclockwise. So I was smelling something, so I don't want to burn it, and it seems that this is not easy to set. This is getting very hot. Not a good option to set the current limit. Now I've connected my oscilloscope probe at the output. Let's have a look at the output ripple voltage. I'm turning it on at 60 volts 4 ampere. And as you can see, the ripple at 60 volts 4 ampere is 523 millivolts. That's huge. Let's make it 1 ampere. It was reduced, at 1 ampere it was reduced to 210 millivolts. Now here for conclusion, we could say that this is outputting 60 volts. Efficiency is very high, to 94%, so it's the most efficient module that I've seen so far. But the higher the voltage, the input voltage, the higher the efficiency. And also in terms of current, if you go with a lower power at the input, then you are able to get 5 ampere, 6 ampere at the output. And here is the list of all values and tests that I did with input and output voltages. If you go above that, the input current, which they have set the limit to be 8 ampere, then you will not be able to get it. Thank you for watching a video from Watt Hour. If you learned something and found this useful, please thumb up, as this will help my video in the search algorithm of YouTube. If you have comment or question, please post it at the comment section below. I try to answer and reply. And don't forget to subscribe so you get updates of my upcoming videos. In this video, we're going to do the review of this Wujie WZ5005 5 ampere 50 volts or 250 watt buck converter that can be controlled also via Wi-Fi of your phone Android device. Now let's turn it on, and here 5.5 ampere is being drawn by my